Okay, I think we are already 36 participants. Maybe we could start already the session. It's my pleasure to welcome everyone to the afternoon section of Multi-Messenger Astrophysics. So we have the first speaker is Razmik Mirzoyan on the recent detection of GRBs at TeraelectronVolt energies. So Razmik, please, you could start the presentation. We see your screen already.
Thank you very much, Narek. I would like to thank the organizers of this meeting, and first of all, Professor Morofini. And I'm happy to make a presentation about our relatively recent work. It will be devoted to recent discoveries of gamma ray burst at teravolt energies. So I think I will say a few words about the gamma ray bursts, very compact. These are very violent, distant explosions in the universe, gamma ray bursts. And then on the right upper corner, you can see a cartoon which shows some of the main processes involved in it. And gamma ray bursts are known to belong to two populations. One conditionally is called short, and the other one's a long burst. And then the borderline between two is 2 seconds. Short are those which are shorter than 2 seconds. And the mechanism for this burst seems to be distinctly different. So while for the long burst, one assumes that the responsible are massive star collapses, which produce ultra-relativistic jets. In the case of short bursts, one believes it is consistent with a binary neutron star merger. So until recently, there was no detection whatsoever of gamma ray bursts in the teraelectron energy band. And then the highest energy photon was one single photon measured by Fermi-Lat instrument at 95 GeV in the year 2013. So from the very strong GRB in April 27. So there is no very strict division in time between prompt phase and afterglow, and then prompt phase of a GRB is characterized. Now I will talk about the long GRBs. Its prompt phase is characterized by structured emission, which can take from seconds to many minutes, and it is followed by afterglow. So in the past, there were a few hints just from GRBs measured by few instruments, which are now only of historical importance. I cite here a measurement from the aerobic instrument, which claimed to measure a GRB event above 20 teraelectronvolts. This was the event which happened 1992 on 25th of September. I was part of this experiment, HEGRA experiment. Aerobic belonged to it. And then I will not go into the detail to save your time, but I give you some main information about this event. From today's point of view, when I look again to this event, I would, with high level of confidence, claim this was not a gamma ray burst event. It was some sporadic event. So 2.7 sigma is not very high to claim signal. Anyway, I think we understood it already back in time now. Another event was from the so-called Milagrito detector, which was a very, very small detector, 42 meter times 42 meters. It was a predecessor of Milagro detector, which itself was a predecessor for a Hawk detector. And then they claimed to see some GRB event, maybe. And there are two publications, one in the year 2000, the other one in 2003. And if you look to details of publications, you can see, especially in the second publication, the big skepticism of the authors by themselves, who could see that there is much, so let's say, by the order or 2 orders of magnitude higher energy emission allocated at GV energies compared to X-ray energy domain, which was not probable. So it was clear that this is not a real event. So these are just of historical importance. That's why I mentioned. Nowadays, there are several instruments which are operating at electron-volt energies. And then these are Cherenkov telescopes, Veritas Hayes Hawk, Veritas Hayes Magic, but also water Cherenkov detector Hawk, and then LASSO, which is a complex detector. And all of them, they are pursuing this program to measure transients like gamma ray bursts, gravitational wave sources, neutrino, target of opportunities, and so on. So there is one distinct difference between these type of detectors. While for wide-angle detectors like Hawk, it is a very easy game just to measure GRB. It just needs to happen in its field of view. For the narrow field of view instruments like Cherenkov telescopes, this is very, very improbable. So what we are doing, we are tuning to satellite alerts, alerts from satellite missions, typically in X-ray range, and then we build our telescopes with a fast slew possibility, and then we start tracking this alerted position. This is how things are working. And then nowadays, all the ICTs are optimized their operation for such a way of slowing. And then, nevertheless, there are differences in the design. So let's say the fastest one until now is a Magic telescope. Already in 1998, it was designed to follow GRBs. And so we were chasing the problem when the telescopes were built for a long time. So there were no results until recently, and then we were lucky, and then I will talk about this good luck. So in the issue of Nature from 21st of November, 4 articles appeared in the same issue devoted to GRBs, and then 2 articles were published by the Magic collaboration. These articles were devoted to the gamma ray burst 1901-14C. Which was the first ever gamma ray burst measured in the TeraelectronVolt energy band. Details I will show a little bit later on. In the first paper, we showed the technical measurements and that this is not a synchrotron emission. I will say a few words later on. But in the second paper, I think we studied the spectral energy distribution from this gamma ray burst by using data of multiple instruments. And then I will come to this point a little bit later on, a few slides later. Also, our colleagues from the Hayes collaboration measured some signal from GRB 180720, a marginal signal on the level of 5 sigma. But the measurement was very interesting. I will describe a few things about it. And then all these 3 articles were accompanied by kind of comment article from Bing Chang about extreme emission seen from gamma ray bursts. And these are the Magic telescopes. Many of you may know about them, at least in relation with GRB 1901-14C. So it is a twin telescope system with 17-meter diameter and 17-meter focal length. They are separated by 85 meters. They are located at a height of 2,200 meters on the Canary island of La Palma. On this height, there is a European North Observatory. So there are over 20 telescopes located there. On the right insert, you can see the imaging camera, open imaging camera, which consists of 1,039 photomultiplier tubes. And lower right corner, you can see laser indicators attached to mirrors for adjusting the mirrors. So there is a lot of automatic operation in this telescope. Here I would like to show you a short movie. This is how this telescopes are operating. So as from the beginning, they were designed to have a fast slow mode in order to catch GRB, possibly in the prompt emission phase. You should think about that. The ideas were crystallizing 1994, 1995. And then with time, we learned more and more. But you can see how during daytime, when we do a test, we can follow an arbitrary position in the sky. We can catch it within 20-25 seconds. So in the middle, you can see the so-called experimental house, where the information from both telescopes is coming via optical fibers. And these are high-tech telescopes with a lot of new technology. For example, signals are coming in an analog way, but we fed them into optical fibers by using laser modulators. So there are a lot of fancy things, some of them which became standard for the discipline. So we are using a fully automatic system for following the transient alerts with MAGIC. And then this includes a lot of software development, but also some hardware, and the safety was always in the first place. Because when a GRB alert comes at an arbitrary time, then software is checking if this is appropriate for us or not. We have our own criteria, then I think a lot of things should happen. So I think it will lock the fence around the telescope. We should be sure that there is no human being around the telescope. And then I think while the telescope starts moving in a very fast mode to the target position, it does a lot of things like adjusting mirrors to the new position. All the mirrors are sitting on stepping motors. And then it's closing the files of previous measurement, calibrating the telescope pedestals and so on. And then for polishing this way of operation, we were issuing fake alerts for the shift personnel once during a shift period, which is typically 3 weeks or 3.5 weeks. And then this has helped us to debug the system. So just a little bit of statistics, GRB follow-ups. So you can see that in the past years, we could follow 105 GRBs. And then typically we were reacting to 8 to 10 GRBs per year. Stereo observations of GRBs. I think we started with after upgrade of the telescope in the year 2013 with higher sensitivity. And then we reacted to 4 GRBs which had a redshift below 1.5. On the left lower corner, you can see the redshift distribution of sources where we got the alert. And then on the right lower corner, you can see the zenith angle of these GRBs when they happen. This is an important parameter for us because if the zenith angle is very large, then the threshold of the telescope goes higher up. And the detection rates are lower, and then maybe significance of the signal will be difficult to obtain just because of statistics. And then you can see on the x-axis on the same plot time delay for the start of the GRB. This is just in order to get an impression. So, and then on this list, I show a table with 4 GRBs, and then 3 of them are of short type. Short type are those below 2 seconds. One of them, this is the GRB that I will talk more about it. This is 190114C. It's of a long time. So I think if I go to statistics, it is interesting only for specialists because we are trying to learn the lessons. When can we measure GRB, how, and so on. So I'm not sure if it is so important for you. And then good luck happened on the late evening or night of 14th of January 2019. And then we got a signal from this GRB. We followed a swift alert. And then I got a call from La Palma, from the swift crew. And then they used to tell that they can see a signal growing up from the online analysis on the monitor. And they were bluffed if this is real or what's going on, because there was no time to think about. Everything happens automatically. And the operator cannot interfere, should not interfere. Anyway, so I think from the online analysis on that evening, we saw something like 20 signal signal. And then just within a few hours, I issued, with the help of my colleagues, after exchange of 64 emails and many telephone calls, in the middle of the night, I issued an astronomy telegram and then GCN circular about this detection, which you can see here. Big signal measured from this object. So our measurements, I think, started after 50 seconds after the start of the GRB, but for technical reasons, we are using data starting 1 minute after the GRB. So I think the measurements were a little bit problematic because the moon was up, but during the past years, long ago, we learned how to measure during the presence of moon, which is somewhat unusual for Cherenkov telescopes. Also, the observation zenith angle was about 60 degrees, but it did not bother us because we developed also the technique to observe sources even to zenith angle of 80 degrees, almost to the horizon. And then it took us some time to realize why it happened during the moon at large zenith angles. And although the explanation is very primitive, nevertheless, I think we were bluffed a little bit. It happens at the large zenith angles because then solid angle is large. So I think your chance probability is large to catch a GRB. And it happens during the partial moon time because observation time is higher. Typically, an Cherenkov telescope observes 1,000 hours per year during dark nights. But if you add up partial moon time, then you can increase this resource by another 30%. So we had both pleasures, yeah. Partial moon, large zenith angles. So, but we were prepared for it, so there was no problem. So we managed to, because of these two factors, partial moon and the large zenith angle, our observation threshold turned out to be 200 GeV, relatively high, while we can measure sources above 30 or 50 GeV, depending on the trigger. And you can see a little bit statistics. It's an average analysis. This is not the best analysis. This is what entered the conservative into publication. This result has been obtained by 10 independent analyses, I should mention. People were very enthusiastic. Typically, for people in different locations analyze the same data independently. In this case, 10 people jumped onto this. Yeah. So we measured something like 50, 60 sigma signal from this source. And then if I go to the next page, I think I showed the detection rate of gamma rays from GRB 190114C on the left U graph. And then on the right, I show the detection rate of very high energy gamma rays from Crab Nebula. Crab Nebula is the strongest steady source in our galaxy. Typically, we measure 6 events per minute from Crab Nebula, let's say at a threshold above 200 GeV. Now let's look in this movie what has happened during the detection. So I should mention that the y-axis of the Crab Nebula is multiplied by factor 10 in order to be able to show what's going on. So essentially there was background-free detection of gamma rays. We had a huge rate of gamma rays on the left one from the GRB, while Crab Nebula was barely moving, and then our strongest galactic source was barely visible. It's barely visible on this plot. Anyway, this was a cool thing, and then I think when we estimated the highest rate for the first 30 seconds, we saw that the intensity of GRB was 130 times higher than that from the Crab Nebula. And then some of us were speculating what could have happened if you would have touched this GRB just in ends from the beginning in the prompt phase, then most probably all the system would saturate. But this did not happen yet, maybe in future. So our colleagues from HES reported 4 months after our detection or after our detailed GCN messages in Bologna. There was a CTA symposium in May 2019, and they showed some that they managed to measure 5 sigma signal from another GRB, which happened earlier than our GRB, but in my impression, I think they started reanalyzing the data after seeing that we could successfully measure gamma rays from a GRB. And then this is what you can see. I think the remarkable thing about this detection is that they saw the signal 10 hours after the inset of the GRB. So this is, I think, very impressive. And then this is detection of this GRB by different instruments. You can see different instruments here, and then by the red dot, you can see in the right middle place on the view graph, you can see detection of this collaboration single point here. They may manage to measure signal between 100 and 400 GRBs. So we were preparing our telescopes well in order to measure gamma ray signal long ago, but I think providing very low threshold of detection, keeping in mind we are going to measure gamma ray burst about 20 GeV, 30 GeV or something like this. So we were optimizing everything. But it happened order of magnitude higher energies. So we're trying to digest that this was a surprise. But then we digested the surprise, and now we know better what one should anticipate. So this is on this view graph on the x-axis you can see the time after the onset of the GRB and then measured by magic flux. And then you can see that we started measuring in reality, I think data acquisition system, DAQ, started at 58 seconds after the onset. So we missed these nice peaks, which saw, for example, Swift mission. Yeah? And then we could see this smooth decay. And then on this view graph, you can see the afterglow phase of the GRB, which we detected. And then you can see that the magic data shown in red dots goes in parallel with this magenta line showing the Fermi-Lat measurement and then XRT measurements between 1 and 10 kilo electron volt. Already here you can see some correlation between them. And then on this view graph you can see what did we measure, and then when we normalize it to the extragalactic background light correction, how the spectrum becomes. So we used one of the trustworthy widely used EBL correction methods. And then what is interesting, at 1 teraelectron volt, gamma ray signal was attenuated by 1,000 times. Despite this, we measured signal until 2 teraelectron volt. In our recent publication, we could prove this 2 teraelectron volt signal. So this is just to show that the signal goes to 1 TeV, 2 TeV. It's of technical help, and then that it is not it is well above the so-called burn-off limit. So it is of different origin. And then this different origin, I think, has been discussed in our second paper in Nature. Second in the sense papers appeared simultaneously, but here we were working with a lot of instruments, and then 24 of instruments, and you can see data from very, very different instruments shown on the view graph, where on the x-axis is shown time after the onset of burst. And then on the y-axis is shown flux in hertz per centimeter square per second. And then you can see a very, very full picture here, complicated picture. And then when analyzing this picture, I think it is interesting, I think, to see a lot of instruments participating in this measurement. I will jump to save time who did what. But as a result, I would like to show you this view graph, which is a remarkable one, because it shows these two amps. Yeah, you see on the right-hand side, you can see a teraelectron volt energies, a new amp, and this is brand new. I think it was long speculated that maybe GRBs are emitting teraelectron volt gamma rays, but because there was no measurement, it's remained as a speculation. Now we proved, and the situation is very similar to active galactic nuclei when in 1991, People telescope by measuring signal from the Mark Item 421 showed that there is not only synchrotron emission, there is also emission of teraelectron volt bands, and the second amp is popping up. So this is a remarkable feature. And then it shows that there is more energy in the GRB, and that it was underestimated the total power of GRB, and then I think it speaks about the mechanism. So Recently, we did another study based on this data about the Lorentz invariance violation. And then I'm sure that most of you know details about Lorentz invariance violation. What is it? And then to put it in a very simple way, I would say that the speed of energy particles under certain conditions could depend on the energy. So that is one theory, and then nobody knows how real is this, or it has a link to reality, but I think these theories exist. And then when one does simple calculation or estimation, I think one can see that by assuming that, for example, two photons are emitted promptly at the same time, at the same moment from some object at very large distance, because the photons travel very long time, let's say billions of years, billions of years they are traveling. I think they get, if their speed is a little bit different, then you will get somewhat different detection times for these two photons. And then I think this can be estimated from this lower right corner formula, simple formula. This is the time difference between two photons that you measure. If their energy difference, delta E, is, let's say, E, for example, 2 TeraelectronVolt and lower energy 100 GeV, and this will be your delta E, and then this is normalized to quantum gravity energy scale, and the parameter D here stands for the distance. So it's includes the information on the source detector convex distance. And there is some parameter S, and then N, and then depending on first order Lorentz invariance violation or second order, I think people are typically considering this too. And this is a simple cartoon to show that when a particle has higher energy, this top one, the red one, it interacts stronger with the vacuum while moving forward. So because of strong interaction, it is held by this interaction and slows down. So this is kind of easy way to explain, let's say, on the level of intuition, what's happening. And then I think you can see this on these tables, the measurements, what has been done, and the evaluated results paper appeared recently in PhysRev. In the lower table, you can see what has been measured, what are the outstanding numbers as of today. And then these are GRB 090510, Markov 541, and then GRB 190114C. So 3 different GRBs. And then they are somewhat very different from each other. So our colleagues from HES, for example, measured signal from Markov 541 until 20 TeV, while in GRB we measured until 2 TeV. So here they get factor 10 in the energy difference. Yeah? And then the redshift, but we get redshift much higher than compared to Markov 541. So in the end, I think our results are comparable to those found out by HES. But the best number from a linear approximation of Lorentz invariance violation is coming from Fermi-Lat collaboration from the GRB 090510. Yeah. But in the quadratic approach, our numbers are as good as from competitors. So we are from the frontier line. So I do not have time much to go here, but looking to this view graph again, you can see that you can see this smooth curve, and this smooth curve was not so helpful for Lorentz invariance violation studies because there was no feature here. And then I think we did intelligent studies. Those of you who are interested can have a look into the paper. But if there would have been a bump or structure or something that we could have had in our hands, I think the limits would have become much better. But this is not the case as long as you measure smooth afterglow. Still, I think in the quadratic approach, I think we have a very, very interesting result. The other GRB, I think another GRB has been measured by the HES collaboration 1 year ago. And then all what we know about this GRB that I think they measured it 4 hours, 20 minutes after the onset of GRB, but it's a very nearby. from the redshift of 0.07. And then I think they claim that they have signal stronger than 5 sigma. Then we are tuned to see results of measurement of this GRB, again, afterglow phase have been measured there. And then here I want to come to the end of my presentation, and then I would like to say a few sentences about the GRB, which happened on 16th of August, 21st of August in 2016, 4 years ago. And then I think you can see from the shown sentences that there are just 20 events detected in the GeV band, and then this is a short GRB. I think catching short GRB is some kind of exclusive thing by a narrow field of view detector, because somehow it takes at least maximum 2 seconds or shorter. Now we can look a little bit to the details, and then this GRB is residing at the redshift of 0.162. So this GRB emission was followed by several telescopes, and there are detections reported from radio, optical infrared, soft X-rays. I think Fermi lat in the GV range produced limit, and the optical infrared observation clearly revealed the presence of a kilonova. So this is what we believe about the short GRBs, neutron star measures. And then I think it was dominating the emission at about 1 day. So after the burst trigger, it takes about 13 seconds for satellite to generate the alert and to send to Earth. So we got this alert after 13 seconds. So it took us only 11 seconds to through the magic telescope and start observing this GRB position. So 24 seconds. It was the fastest ever we did.
Razmik, sorry, you have 2 minutes left.
Yeah, I'm finishing now. I think this is, I will finish with this one. Yeah, thank you. So I think T90 of this GRB was believed to be half a second or 1 second, depending on the detector. And then weather conditions initially were not so good, and there was a bright moon. But still, I think when we did a honest analysis, we came down to 3 sigma. Here, I should tell you that initially we got a signal of 4.7 sigma from this source, but it was shifted a little bit from the source position by 0.05 degrees. And then we did a lot of studies to understand why the position is shifted by this amount. And then it turned out our today's explanation is that in the presence of a weak signal, we did a lot of Monte Carlo studies. This could happen, that the peak position of the signal is shifted by a small amount. But I think here you can see the excess, which is quite small. And then this is the honest significance. I think the paper is just ready for submission. It is under collaboration review. But I should mention that this result is produced by using the standard analysis technique. And then we are using now novel analysis technique, which reveals higher signal level. And this work is under preparation. I think these are takeaway messages from these detections, but I will stop here. Thank you very much for your attention.
Thank you very much, Razmik, for this very detailed and very interesting presentation. We enjoyed it very much about the GRBs. We have a time for some questions. Is there any question from the participants? Well, if not, I have a question. I mean, since now it is confirmed that there is the second bump in the GRB spectrum, what do you think when there will be this next generation of Cherenkov telescopes coming, like LST or CTA? What would be the number of the GRBs detected per day? How it will change the field, I mean?
Well, I think it's a complicated question, Narek. I think I can do some arithmetics.
Yes.
I will need to communicate it to you. I cannot answer now online, but I can bring some considerations about this. So some of my colleagues are very optimistic that with CTA one will measure much more many GRBs. I am skeptical about this. So I think not very much will change. So what will happen? I think we will measure these GRBs in the afterglow phase regularly. So this will become a regular type of sources for actually for telescopes. But their number will stay relatively low. And you see, if some GRBs could be measured 10 hours after onset of GRB, then I think it makes quite realistic with the current sensitivity to catch up this GRB afterglows at a late time. So in this way, I could imagine that the number will increase and then steadily will increase. It will not explode. And why I'm saying that I do not anticipate much more many GRBs to be measured by CTA compared to current instruments, because you see what is happening. I think GRBs are not happening as a rule at the lowest threshold. So you make an instrument with 20 GV threshold, but the GRB is happening at large zenith angle and at the presence of the moon. So in the end, your threshold is 200 GV or 100 GV. So this is limiting your reach in the space. So I think the volume will not increase that much. It will still increase because I think you will have relatively lower threshold, but no revolution will happen. So I think, and I think before CTA telescopes will start producing such data, I think current instruments, active instruments, will still measure some GRBs. So you know very well that whenever GRB is happening, I think people are keen to direct the telescopes immediately. Let's say an average number is something like 2 GRBs per year. Yeah, that we can measure with such telescopes. But with afterglow, maybe the number will be around this number, could be slightly higher. And then it will stay so until we will invent a wide-angle instrument, I think, that can measure at 100 GV or 50 GV or even lower.
I see. Very good. Thank you very much, Razmik. Indeed, the observation of the magic or the HES already were revolutionary to find this second component. So there is a lot of already to be done for the GRB science, right?
Yeah. Yes.
Okay. There is any question from the participants?
I just want to make a short comment. I think I did not stop on the theories which were extensively shown here. That my colleagues around Remo Ruffini are pursuing because of time reason, but I think they were shown extensively. So I just showed things from the narrow point of view, how we do see it from the side of experiment.
Thank you very much, Razmik. Thanks once more. So now we move to the next speaker, which is Vladimir Lipunov, Central GRB Engine from Early Multimessanger Observations. So please, could you share your screen and start the presentation? I think your microphone is muted. If you could unmute, okay.
Yes.
Okay, now I see that your microphone is unmuted and we see the video of your camera.
Okay, I will start.
Okay, very good.
Okay. Thank you very much, Remo, and all people for the possibility to talk, to give a talk at this very nice traditional conference, the GRB conference. Today, I would like to say about the central engine and multi-messenger observation. The voice is good? Yes? Okay. Maybe yes. My talk is partly observational and partly theoretical. So the first part is observational, second theoretical, and after that I come to the observation for some theoretical testing. Okay. That is my co-authors from the different country, the main number from Russia, but from different city. Because today I would like to say in general about the global master network results. And by the way, that is a very old photos of the relativistic astrophysical department of maybe I can move this. Yes, this is good now. Maybe yes. No. Hello.
Yes.
All okay. Okay.
Yes, yes. We see your
that
slide.
That is our department. You see, Ya.B.Zeldovich. That is the middle of 1980s years. He founded new laboratory. He has 3 or 4 laboratory in Moscow. There's Leonid Grishuk, Mikhail Sargent, the general relativity theoretical people. This me, this Nikolai Ivanovich Shakura, Sergei Simakov, Sergei Kopeikin is a professor of the Missouri University now, and Sasha Petrov. That is young, more or less young people near the teacher. Okay. And come back to the started from observation. And the global master network now occupied several very important longitude and latitude. You see 3 points near equator, but the south hemisphere, and a lot of points in Russia, because weather is not good, but we have the several telescopes very near, and so. And this telescope can observe in different way. The first way is the discovery, the survey of the sky and discovering object. Another type of observation is the alert observation. Today we will be discussing exactly alerts observation, because the main object, our object is gamma ray burst. And you see, we discovered about 10 different optical transient on the sky. And just a moment. Something wrong. Just a moment. Okay. You see here some part of discovered our transient. You see because global geographic, we can discover the object on the whole sky. You see there's a south sky, that is the northern sky, there's a Milky Way, you see. And you see here different objects from the solar planets come to the very high 10 billion light years from the Earth. Okay. And here I would like to show you our interaction between different telescopes. Red arrow, maybe red arrows is alert from the gamma ray observatory, well known, but when we discovered some object, we give alerts from different very large telescopes in the world. But last 3 or 4 years, 5 years, we started to observe different alerts from the very big physical experiments. You see the gravitational wave, that's LIGO-Virgo collaboration. And we discovered independent. We have this independent discovery of the kilonova. I'm sorry. And we interact. We have a lot of alerts from the IceCube. And once we detected very close to the optical changing of the blazars, I'm sorry, this, I would like to show, maybe people knows this paper recently appears in Astrophysics journal, and optical reveals strong evidence for high energy neutrino. And recently we participated in work with fast radio burst, and this preliminary, I show preliminary our very huge run of observation, optical observation with higher time resolution, very well-known fast radio burst. This one, this is recurrent radio burst, and we receive a lot of results, and we received 150,000 images, and maybe now in the preparation. This paper is prepared, but we sent to the Astrophysics journal this paper. But come back to gamma ray bursts. Gamma ray bursts observation based on the gamma center network. You see new slides, not maybe. No. Just a minute. You see here. Okay. This well-known site, gamma center network, and now we receive about, during the 1 year, we have the telescopes, and we have about 1,000 alerts pointing during the 1 year. So you see our telescope is very light to binocular. This only one in world polarizer telescope, wide field polarization telescope. And we have 3 axes. When we have alerts, we can take simultaneously 2 images in different polarization or different colors. The interesting object, very, very quickly presented. You see the observation, early observation of gamma ray bursts 5 or 6 years ago. We come to the leader of the early observation. That is our observation. That is from the Alan Claude Stock. And that is Rotsy. You see Rotsy, but now we installed 3 very nice place telescope. Recently, in this year, we published result of observational, not maybe successful because some gamma ray bursts not give the optical, but 130 gamma ray bursts. This is a reference. And you can see next one graphic. This common distribution of the number of GRB among the time after trigger. You see, this is the first minute, and you see here that is the swift pointing, and you hear the master is the leader of the first minute observation of gamma ray bursts. Of course, we observe usually in the polarizators, but telescope not very big, 40 centimeters, and we can detect the polarization only bright, maybe brighter than 14 or 15 magnitude, only bright GRB. And I discussed several results last year, published in different journals. The first our analysis of the optical, you see, we collected the best light curve of gamma ray bursts from the early point of observation. You see the good light curve, the number of good light curves is very small. Here you see the best curve detected in all 30 years, no, 20 years observation of gamma ray bursts. There's only about 10, and half of them master observation. You see, we pointed before optical appear, and we see the light curve as this afterglow, as this is sometimes synchronously with gamma ray bursts. But you see the different light curve is differences. Light curve is about several orders. You see here there's about 1,000 in the flux and several hundreds between maximum in time. This time between time after the trigger. And you see, if we come new coordinates, this is the normalization time, not depending from redshift, as it is the normalization to maximum optical curve of gamma ray bursts. You see, we discover is a special type of the smooth optical self-similar emission. You see the shape of optical type is very similar in this coordinate. No redshift here, not depending from redshift in this picture. And I usually people say a lot of light curve with very complicated shape. But I remember the Auguste Rodin, the sculpture. He say, I take a block of marble, and cut off everything that is unnecessary. You see, and best light curve you see here, and come to this new coordinates. You see universal picture. Okay, because the real process is very complicated, and the most important process can be fall under the noise, as theoretical noise. This theoretically clean situation and predicted by very early 19 papers on the jet emission. That is a very important gamma ray bursts of last years, 1 year before. You see here, and a lot of paper published in Nature and in very good journals. But I would like you say that the first time master from South Africa, first observed optical emission, and with the 4 polarizators. It's unique situation when the 2 telescopes from South Africa and Canarian Islands pointing to the 1 GRB. And we received several results now published. You see here in this Astrophysics journal letters, and you see this gamma ray, this multi-messenger, real multi-messenger astronomy. That is our optical observation, this gamma, this X-ray, and these three different spectral situations. But unique result, our unique result, because we point very quickly, we detected polarization. You see this from paper, our paper with Mandel and his collaborators. You see our point, 8%, and after 200 seconds, no polarization exists. no, 2-4%. That is very, very big error. That is a fault. Liverpool telescope after 200 seconds pointing to this, and our common publication. You see, we receive the Swift detected gamma ray bursts, and after that we receive coordinates to two telescopes, 6,000 kilometers simultaneously come, and we have the four polarizators, and we have all Stokes parameters of this gamma ray burst. That is our, you see, that is our non-published light curve and polarization. You see polarization changing and come to the interstellar, the Liverpool. As that you see four simultaneous images of the gamma ray burst in four polarizators. Unical, okay. Next one, very interesting gamma ray burst. I now have no time, a lot of time, and I show you only interesting gamma ray bursts. We discuss it now, and you see this in previous talk discussed, and we detected that very nearest gamma ray burst, very nearest, about 336 megaparsecs, you see, but nobody pointed that I will say now later. You see, this very interesting possibility. This is our light curve, you see, very nice light curve. And I would like to stress your attention that at this time works one of the LIGO-Virgo collaboration gravitational wave spectrometer. And usually gravitational wave spectrometer can detect a gravitational wave from black hole, emerging black hole, of course, the distance much more than the distance to this galaxy. So we have first limit for gravitational wave from gamma ray burst. The answer, no gravitational wave at this moment. You see here, that is a LIGO-Virgo state or at the GRB moment, and you see at this moment Virgo and Livingstone detector works. And we have the upper limit of gravitational wave. First in time, a real upper limit of gravitational wave from the long GRB. The same, you see here the same this well known. Okay, about theory. I want to discuss it very quickly. The general point, my point, and maybe not only my point on the problem of gamma ray bursts in the general picture. And we come to with energy, we have no problem to explain this is a typical collapse energy, 10 to the 51, 53 of all the mass, 1/10 mass, solar mass, no problem. The Bogdan Paczynski firstly point out this, the gamma ray bursts must be cosmological. So, you see several, the Bogdan Paczynski collapse of the massive star. You know this paper, okay. Energy, no problem. Spectrum, yes, more or less. The Y-peak, the 1 MER, typical temperature in collapse. In the neutron star surface, in the black hole surface, the typical temperature. But I don't want to discuss it. Duration, this is very simple. The long GRB and short GRB from 101 to the 100, and more from the duration of the engine. The typical collapse times, billion RAS, not billion, million RAS, less than the observed time. So That is the main question. Why? One solution that we have the collapse in the time scale of the magnetic rotational collapse of the formation of black hole. This first magnetic rotational collapse, this time the momentum, angular momentum, the moment of force. That is the formation of the disk-like object and diffusion. And maybe Ruffini and company developed the self-point on this gamma ray bursts. That is the time accretion to the from supernova envelope in binary system. So three scenarios we have for long GRB. Mostly scenario. First collapsed black hole. You see that's very, very qualitative picture. Formation black hole, formation massive accretion disk, and time of GRB is equal to the time of diffusion time, accretion time in disk. Spinard scenario. I like this scenario and proposed a lot of years ago formation object spinard and formation after the first step, the formation spinard, and second step, formation of cap black hole. And the Ruffini team developed the model of formation. Oh yeah, I'm sorry, that is maybe some mistake. Here the firstly format, we have the binary system with, for example, neutron stars and the usual massive stars which collapsed, and you know this in the first lecture on this on our symposium. So spinard, what is a spinard? The my sentence next. First time during the magnetic rotational collapse, if you have the big angular moment, firstly, collapse stopped by the centrifugal forces. This idea very old. I have no time for this. If you people want to know the history. In several years, 10 to 13 years ago, we described this model. You see, if you have the massive star, very fast rotating and collapsed, I think the Pyre collapsed of very massive 50, 90 solar mass initial 100 stars, and very big, very large angular moment prevents the collapse. And we have the first shock that is a precursor when the spinard comes to the quasi-stationary state. After that, due to the magnetic, for example, field dissipation of angular moment, we have some long time gamma ray burst, and second, that is a gamma ray burst activity. The activity of gamma ray burst finished after the collapse of the central formation of the limiting Kerr black holes. We proposed the qualitative models, and you see here, we see this small.
Sorry, you have 5 minutes left. You have 5 minutes.
Okay, that is very simple qualitative picture. That is the viscosity of the which magnetic energy maybe viscosity. That is the specific angular moment like to the artificial Kerr parameter. If the Kerr parameter, effective Kerr parameter, less than unity, you have supernova. In another case, you have short, long gamma ray bursts with plateau and so on. you see this model included all relativistic effects, including the disappear of the magnetic field and gravimagnetic forces, so expirement, all included. You see that is a plateau, and we have the very two-order fall of the luminosity, which we cannot understand in other mechanism. So Spinar is very critical from some theoretical, but last years appeared three-dimensional computer simulation which shows the Spinar is leaf. And now we simulated the different precursor time and the energy of the gamma ray burst, and people can be see. And now we preparing new Spinar consideration, and we include dynamo mechanism. And last of several minutes, I would like to say, or be very bright, 16 years, 4 years ago, the 2-hour telescope detected, but unfortunately in polarization only this telescope in Canarian Islands. You can see our observation. We started before gamma ray burst occurred. This real upper limit, that is optical synchronicity with gamma, this moment of gamma ray trigger time, you see. And I would like to stress, you see the quasi-periodical some, not very significant, of course, but we have the mathematical analysis, and this shows that we have maybe some quasi-periodical sources, process. We use this observation as argument for the binary, for the binary nature of the gamma ray burst. We use it to model. That's very important because in Spinar model we need a lot of angular moment which can be in very close binary system, contacted binary system, and with period less than half a day. And in this situation, in binary systems, this central star have the very far, very big angular moment, not immediately formatted the black hole and Kerr parameter, mean Kerr parameter more than unity. And when the jet comes, we have the moving jet through this spiral function and produces such picture, which we observe. This first model, you see here, that is a typical. The observational is very good, and this real physical variation. Maybe another model may be received from the Ruffini model after several days. Maybe we discuss it with Remo how we can include it in our paper discussion about the model of Ruffini. In any case, in binary system we have non-homogeneous stellar winds before collapse of the more massive companion. This model A, you see the very close binary system produces the sun. That's very simple model. Gravitational wave, gravitational forces is distorted of the stellar wind, and jet moving with very high velocity and produced variation on the scales several dozen seconds. You see, several dozen seconds, because stellar wind's velocity is much smaller than the jet velocity. a model for stellar wind, and we simulated such behavior. And problem of the first model, this model that the ring orbital in the equator, but jet may be produced perpendicular. And so we consider another model when the second component move on the elliptical object, and so the disturbed the periodical stellar wind or ejected the shells. And the jets, you see here, result of calculations, the model B, not very fast. You see here that is a relative density of stellar wind. You see quasi-periodical, not periodical, because the stellar wind velocity is changing. You see here longer. There's a radius in solar radius, and divided to the, you can divide it to the speed of light. You see that the 100 seconds, not more. And we have some approximation of the process for these parameters. And conclusion, we considered the model of maybe this is one of the first, not strong, but maybe first manifestation of binarity of the gamma ray burst. The people can become to my appendix. You see very nice 11 optical transients, firstly discovered by Master in this year. Very nice. If the people want the light curve and the common paper, welcome to us, because now we publish it only the Gamma Center network telegrams. This is our young people in our laboratory. Thank you very much for attention. I'm finished.
Thank you very much for this nice presentation. We have a time for a very short question. Is there any question? I don't see that anyone typed in the chat any question. Moreover, we are running out of the time. So I thank you again once more for this nice presentation. And now we move to the next speaker, is Joanna Kiryluk, high energy neutrinos latest result from IceCube. Please start to share your screen and start the presentation. I don't see if Joanna is online. Oh, yes. Okay. I cannot hear your voice. I don't know if your microphone is muted. Okay, now I see the camera.
Okay, so now you should see my full presentation.
Yes. We see it. Please start. Okay.
Okay. So I'd like to thank for the invitation. It's been a great pleasure to present the latest result from IceCube. Neutrino astronomy has started with the discovery of neutrinos from the supernova in 1987. 25 years later, IceCube reported the discovery of extragalactic PeV neutrinos of extragalactic origin. And a few years ago, the neutrinos, high energy neutrinos, were found to be pointing to a blazar, which was in coincidence with photons, gamma rays, the blazar was in a flaring state. So with neutrinos, one of the goals, in addition to multi-messenger astronomy and looking for coincidences with traditional optical messengers and also gravitational waves, we would like to expand the observational universe towards higher energies and larger distances. So this region here marked as black indicates the part of the sky that's opaque to photons, and this is because high energy photons interact with EBL or cosmic microwave background, and basically they are not visible. So IceCube experiment is the only 1 cubic kilometer experiment that has so far detected these PeV neutrinos. It's instrumented with 5,000 optical modules. It spans 1 cubic kilometer. The distance between the strings and the optical modules deployed on the strings were conservatively chosen to and optimized for the optical properties of the ice, such as absorption and scattering length. In addition to IceCube array, which is buried deeply in the ice, you can see the deep core, that's a smaller array that was built in with a smaller optical module spacing, primarily aimed to pursue oscillation physics with atmospheric neutrinos. With IceCube, we cannot detect or reconstruct individual flavors of neutrinos, and we're not sensitive to neutrinos and antineutrinos, with one exception that's called glacial resonance. Instead, we observe a few event topologies. One is called track. Tracks are produced, muon tracks are produced in charge current interactions of muon neutrinos in the ice, and optical modules detect the Cherenkov radiation from the muon propagating through the ice. The advantage of tracks is superior pointing resolution, so they are primarily used for searching point sources. The energy resolution, because we're only observing part of the track in the detector, is worse compared to the other signature, which is called cascade. So cascades are produced in interaction of electron, deep inelastic interaction of electron with nucleons, as well as low energy tau neutrinos. And we can also detect products of all-flavor neutrino interactions by a neutral current. What we call a composite is a double cascade. It's produced in, for example, tau hadronic decays, or starting track, which is a signature of muon neutrino, which originates in the detector. IceCube, the main background is atmospheric muons. The second background for astrophysical searches is atmospheric neutrinos, but there are also signals for physics with unique physics with astrophysical atmospheric neutrinos. Atmospheric neutrinos, high energy atmospheric neutrinos, are of high energy. They're inaccessible in current accelerators, so we can do physics at high energies. Typically, neutrino rates for neutrino telescopes are calculated there is a straightforward relation between the flux and the factor called effective area. The effective area takes into account the size of the detector, the probability of interaction, and the Earth absorptions. So with atmospheric neutrinos, they travel through the Earth. We can't really distinguish muon neutrinos coming from the south because there is an overwhelming background of muons from cosmic rays. And the Earth absorption starting at roughly 40 TeV starts absorbing these neutrinos. So at highest energies, we can only see horizontal neutrinos. This is reflected in the plot on the bottom right. So you see the effective area as a function of energy, and there is a strong dependence on the angular direction, whether the neutrinos are coming through the Earth, vertical, or coming from horizontal direction. So those which are verticals are being absorbed by the Earth. With high energy atmospheric neutrinos, this is an important probe to call QCD physics. It's sensitive to hadronic interactions, so we're interested in describing modeling fluxes of atmospheric neutrinos. Hadronic interactions are important. In cosmic rays, we have interaction of cosmic rays with the air. That's fixed target. The information about modeling these hadronic interactions and predictions on neutrino flux all comes from other experiments like PA, so proton iron, PP, and all of these mesons that produce conventional and so-called prompt neutrinos, they are produced in the forward region, so it's basically non-perturbative QCD. The experimental data that's relevant for modeling neutrino fluxes, atmospheric neutrino fluxes, are those from LHC, REC, future fixed target experiments, past HERA-B, the future EIC. In addition to hadronic physics, these atmospheric neutrinos are important for astrophysical neutrino searches, and at lower energy, they are used for oscillation physics. A summary of low energy and high energy measurements of the atmospheric flux is shown on this plot. The dashed line roughly separates the low and high energy regime. So for this talk, the relevant part is on the right. Number 3, this indicates TeV. So above TeV energy, we're basically the experiments that are performing the flux measurements are Antares, primarily IceCube, and there are some measurements by observatories like Super K. But because of their detector is smaller, then the flux drop falls and there's less sensitivity. The atmospheric conventional fluxes are pretty well measured. There's uncertainty from hadronic interactions that could be reduced in future high energy nuclear physics experiments. No prompt component has been observed yet, and it's important for the astrophysical searches. Now, the atmospheric neutrinos, especially muon neutrinos, are important background for point source searches. The first evidence of the source came from the alert of IceCube detecting 300 neutrino events, and there was a multi-messenger multi-wavelength photon follow-up observation of this event. The blazar appeared to be in a flaring state, but a single event does not make a high significant measurement or spatial correlation. So what IceCube did, we searched archival data for neutrino clusters from earlier data collected by IceCube. So this is done by a standard point source search. For this particular source, we used the location of the source, and we searched for an axis of the neutrino signal above the background. So for this search, the background are atmospheric neutrinos. And we found a cluster of lower energy neutrinos than the alert, which was initially triggered the search. So the alert is indicated on the right edge of the first plot. Around 2014-15, we saw the cluster of events. The lower energy events, but they counted for 3.5 sigma significance. So since that alert, there were multiple follow-up searches. So this is in response to alerts issued by IceCube. So we issue alerts on high energy neutrinos with different event topologies. So cascades or starting events that I'll describe in a bit later. And that triggers, depending on the significance and the energy, the multi-messenger follow-up that we've heard in the previous talk about. In addition to triggered events, IceCube searches for sources in the full scale that's without any information from the catalog, gamma rays, and other observatories. So this is typically done by the likelihood method. So we divide the whole sky in pixels, and for each direction we use information about the data and model this, the position of the source in that particular pixel, the position. We have PDFs that describe source characteristics, the background characteristics, and we form a test statistics where in the denominator we have the likelihood constructed depending that there is a source contribution, flux from a source, and in the denominator we have an assumption that all events are come from the background. So based on this, on the search, we found the hottest spot that was in coincidence with the galaxy NGC 1068. I should also point out that all these test statistics, we also have trial factors. So the background is randomized, and we search for coincidental or artificial correlation, chance correlations, just because we don't have enough sensitivity to the signal. So the final significance is called post-trial probability, and that takes into account the search over when we randomize all the experimental neutrino events, and as I said, they're dominated by atmospheric neutrinos, and then find how many of these random maps provide a significance larger than the data which was found in the real search. So the significance is not very significant, 9.5% of trial. In order to increase sensitivity, we usually search for point sources with a predefined list. So this is to increase sensitivity due to these trial factors and looking at the same place multiple times. What is shown here, you see the upper limits, since we didn't find any significantly significant correlation with the source. The most significant ones are the 4 sources. These are the 4 triangles for the declination, sign declination 0. The second one corresponds out on the blue curve. The second one is the XX blazar, and there are 2 other blazars. So these are the most significant sources. For a given assumption on what these astrophysical neutrinos spectrum they should follow, we have a different group of results. The black ones correspond to the assumption that the flux of astrophysical neutrinos is soft and follows e to the minus 3. And the red one is when the assumption is that astrophysical neutrinos follow e to the minus 2 spectrum. We also have sensitivity lines for Antares, which is located at the northern hemisphere, so it's more sensitive to sources which are located in the south. In this case, you can see lower sensitivity for IceCube in the southern sky, just because the atmospheric neutrinos and neutrinos in general are, for this particular research, more significant for the northern sky. Also perform full sky source cascades. So cascades can be reconstructed in full sky, so it's not limited.
Sorry, you have 5 minutes left. You have 5 minutes.
And we have not seen the significant source. Another search was with gravitational waves. The search was performed with 11 gravitational waves events in total. So for this, we used the gamma ray follow-up stream from IceCube. So what you can see for this particular gravitational event, you have blue crosses. So these are the neutrino events that were found in IceCube around like 15 minutes from the event. No significant access was found, and we were able to derive a limit, so a limit on isotropic equivalent energy, which was emitted by the mergers of black holes and neutron stars. They are marked in triangles. So the orange one is for a neutron star, and the blue ones are for black hole mergers. We searched for correlation with neutrinos with ultra high energy cosmic rays. The highest energy cosmic rays do propagate in straight lines, but we didn't find any correlation. The second part of my talk is about the measurement that we were able to make following this.
Excuse me, Joanna, if you don't mind, could you please deactivate your webcam? Because we cannot hear you now. There is a
Yes,
problem
we
with
cannot
the
hear.
connection speed, apparently.
Seems we lost the connection. Joanna, can you hear us? You are unmuted. We cannot hear you.
Apparently, there is a connection loss.
Yes, because I see her camera on, but I cannot hear her voice.
Okay, maybe we can go on with the program.
Okay. Okay, she's back. Joanna, are you back?
I'm sorry.
Yeah, we couldn't hear you. Now we can. Yes, you are here. Yes.
Yes. So
Okay.
shall I go back? I don't know when you lost me.
Sorry, can you please repeat?
Shall I continue with this slide or shall I move back?
Yeah, it was like not so long that we lost the connection. Maybe you could continue from here.
Okay. So one analysis type is called high energy starting events. This was the analysis that led to a claim of discovery of astrophysical neutrinos. This analysis is sensitive to high energy neutrinos above 60 TeV. Another analysis is cascade analysis. This analysis is sensitive to neutrinos that are with significantly lower energy threshold. So all the systematics due to energy scale are reduced compared to the previous one. The summary of all diffuse measurements is presented in this plot. So I just want you to focus on 3 lines. The green one is the high energy starting events. The red one is for cascades, and the blue one is for tracks. So they have relatively large errors. Some analyses have lower errors, lower uncertainties. This all includes all systematics, but they're consistent. What you see on this plot is the cascades is shown, flux is shown as the purple band in the middle, tracks flux is shown as the blue one. What this plot illustrates is the connection of energies emitted in gamma ray background and in cosmic rays. So the fluxes are similar. There are different models. So here I mentioned just 2 that set upper limits on the total flux on neutrinos if neutrinos were originating from the same source as gamma rays and high energy cosmic rays. What you see here, the part of the purple one speaks about the limits set up by this multi-messenger connection. So the origin of these neutrinos is a puzzle. We claim that this was proposed by some theoretical model and estimated before, but now we're confirming that these sources are perhaps opaque to gamma rays and are not visible by the telescopes. This plot shows that the expected galactic component to the total flux is low, so below 20%. We could also expand the diffuse analysis to search for a flavor composition, since all the analysis before assumed the same fraction of neutrino, muon, and taus. but we're not sensitive to distinguish models between like different new physics in the oscillation sectors. So the results are right now are compatible with the assumption that the production is it just comes from the pion decay to muons and muon decay into electron. So this results in a 1-to-1 flavor composition at Earth. And the last topic is from the particle physics. It's neutrino nucleon cross-section. So this is basically, well, it's related to how we detect neutrinos. So the neutrinos that go through the Earth are being absorbed. The probability of the absorption depends on the cross-section. What you see on this plot is the angle distribution correlated with the neutrino energy, and the transmission probability is marked in colors. So the high energy neutrinos and vertical are basically absorbed by the Earth. When the first measurement in energies of neutrinos far above the accelerator data was performed by IceCube with muon neutrinos. We were able to check the scaling factor, how the cross-section will scale compared to the standard model cross-section with the Parton distribution functions that are marked, that are taken from the reference at the bottom. And there were three other analyses that expanded the search and used slightly different techniques to get the energy dependence of the cross-section. So instead of just scaling this in a wide energy range, now we have the beams of the cross-section in the beams of energies. So the change of the cross-section is expected. IceCube would be limited in energy, so the ultra-high energy will not be accessible by the current methods, because the method presented on the left-hand side, because it's basically limited to neutrinos that would be downgoing, since the ultra-high energy neutrinos will be disappeared and will interact in Earth due to increased cross-sections. So there are other effects that may increase or decrease the cross-section. It's important because by measuring the total number of events, we are sensitive to the flux, which is largely unknown, and the cross-section. So if you want to see for effects that in QCD and possibly beyond standard model, that we should be able to disentangle these events. And the last slide is on upgrades. So what's in the future? We're planning to instrument the detector with 7 additional strings. The deployment is planned for the 22-23 season in Antarctica. Here, so the new addition would be new hardware. So we would be testing new optical sensors. So for example, MDOM will consist with multiple PMTs of smaller size than traditional IceCube DOM. The egg will consist of larger PMTs, 2 larger PMTs. The area would be increased, and we want to have a higher acceptance for the light coming from both sides, so above and below, since the IceCube typical DOM just has PMT pointing downwards. There will also be calibration devices, new calibration devices. So all of this is aims to recalibrate also existing data in order to reduce systematic uncertainties. I'd like to conclude with the future. So there is a proposal for the next generation IceCube that would include additions such as radio detectors, beta surface detectors, and you can see a plot here which shows one example of how the sensitivity to, for example, a flare from TXS, how the discovery threshold or the significance would increase with the larger detector volume. So that's all. Thank you.
Okay, thank you very much for this beautiful, nice presentation. Unfortunately, we are really time is 20 minutes late of the time, so we don't have time for the questions, and we directly move to the next speaker. So anyone who has the question could write in the chat, and the speakers could see in the chat and answer the questions. So please, the last speaker of the session is Maxim Khlopov. Please start to share your screen and start the presentation.
Let me do it, please. Yeah, thank you. Thank you. Thank you. And thank you. Thank you. I thank very much everybody for possibility to discuss. Well, do you see my screen? Let's hope yes.
Yes, we do. Yes, we see your screen.
Okay, and do you see the full presentation? Yes, full slide?
Yes, full slide, yes.
Okay, so we discussed just in previous talk multi-messenger astronomy, and in cosmology we may have also similar thing as multi-messenger cosmology of new physics, which inevitably appears in the current cosmological paradigm of inflationary models with baryosynthesis and dark matter energy. And reminding the legacy of Zeldovich, I'd like to say that it is he was not only the person who personally triggered a lot of directions of development in these fields, but also his analysis of links between cosmology and particle physics have revealed many additional model-dependent elements which provide some refined test of the physics underlying inflation, baryosynthesis, and dark matter. From cosmological viewpoint, in particle physics, we are interested in most fundamental properties, like conservation laws related with symmetries, which provide us stability of particles which we consider as candidates for dark matter. The high temperature behavior of field theory gives us prediction of phase transition in early universe, and the transition can give us some topological defects, some macroscopic structures. And also there is a possibility to probe some stages of early universe, which just finished very early, so we don't have direct information about them, but there is indirect possibility probing them by black holes, primordial black holes. So actually cosmological dark matter just assumes existence of something what is non-baryonic and have some specific sufficiently weak interaction. The simplest case is to consider so dark matter in that sense is cosmological reflection of the structure or fundamental structure of microworld. It's fundamental symmetry, because extension of symmetry of standard model gives us a new conservation law, and candidates which lightest particles which possess this new charges, they are stable or long-living, and this conservation law prohibits them to decay, and so that they play the role of dark matter. All the existing examples just demonstrated, because we have a parity in supersymmetry, we have a minority in mirror world. We have Pichet-Quinn symmetry in axion models, and we consider can also consider some macroscopic forms of dark new forms of matter, of non-relativistic matter in our universe. The simplest possibility was WIMP miracle, because so I see that there is some delay of slide relative to what I'm talking, so we have to, I think, wait a bit with my slide so that it is just corresponding to what I'm saying. So actually, if we take frozen out particles of some created being in equilibrium in early universe, then if they are weakly interacting and massive, then at masses about 100 GeV, they can fit the observational data about the dark matter density. And however, direct search of such WIMPs gives uncontroversial results, as well as there is no supersymmetric particles at the LHC. Well, LHC was motivated that some new physics should appear in the range of 100 or up to 1 TeV, just in order to relate it with the nature of electroweak symmetry breaking, with solutions of problem of Higgs boson mass divergence. So it shows that we should go to much wider class of the dark matter candidates, and they may be sterile neutrinos, it may be axions, which are necessary in solution of strong CP violation in QCD. It may be gravitinos, even if supersymmetry is not broken at the 100 GeV TeV scale, it may be broken at Planckian scale, but when it is unification of all the four fundamental forces, and then we may have nice super gravity, Stravinsky supergravity, but such inflationary scenario, which can provide super heavy gravitinos of dark matter, just loses importance of supersymmetry as a solution for the original electroweak symmetry breaking scale or the finite value of Higgs boson mass. And then we can address some other solutions which can give us very non-trivial candidates like multiple charged particles. Today, Timur Bigbayev discussed some specific type of these particles, which are minus two charged lepton-like particles bound with primordial helium. And so it is something that it just involves only one parameter, mass of this hypothetical particle, but it gives us the possibility to just describe all that, because this helium shell of this atom is something what is only related to known physics of nuclear interaction, atomic physics, but the conditions in which all that these known laws are applied are so non-trivial that it really needs a lot of studies to understand what really happens when this dark atom comes to underground detectors. Well, maybe supermassive particles, neural shadow particles, and they follow from different motivations of the extension for standard model. And so one can expect that they can coexist in multi-component dark matter. So actually, what we may treat is that we may have some sources in very early universe which accompany physics of inflation, baryosynthesis, and dark matter, which are created in early universe. And together with these necessary elements, with a necessary model-dependent byproducts of corresponding solution, just gives us what I call multi-messenger cosmology, and its predictions should confront observations by multi-messenger astronomy. So here just I give some idea what happens if we have stable particles or unstable particles. And if your particles are unstable but sufficiently long-living, then their decays are source of non-equilibrium particles in equilibrium of cosmological plasma after first second of expansion. We have some energetic particles which evidently can change processes in this period, just in and was influencing the spectrum of CMB background of CMB, or just cause some changes in primordial chemical abundance. If they decay just now, they are sources of high energy cosmic rays, for example, or high energy gamma radiation. Actually, one of the possibilities to go to much smaller time scales to the very early universe before 1 second is to consider primordial black holes and go just discuss today, reminding mechanism of Zeldovich-Novikov that you may stop expansion within cosmological horizon. That gives you primordial black holes of strongly subsolar substellar mass, because the mass within horizons was very small there. And it corresponds to strong and homogeneity. But if this particle, this dark matter, if these primordial black holes have masses above 10 to 15 gram, you have them as the component of dark matter, and there are severe constraints on such form of dark matter. However, such constraints may be reconsidered, taken into account the possibility that man might be primordial black hole cluster. Primordial black holes are proofs for different catastrophic processes in a very early universe. For example, post-inflational dust-like stage gives us possibility to to remove the exponential suppression of the probability of black hole formation. But it turns out, as we have shown with Sasha Polarov, that this suppression still, we remove exponential suppression, but we have power law suppression, which is sufficiently strong. However, it gives us minimal probability to form primordial black holes at the stages of dominance of super heavy particles. If there are some super heavy metastable particles, they can dominate in the universe. At this period, you have formation of objects correspondingly small mass, but these objects just possess all the property of development of gravitational stability in this period, and there may be primordial black holes formed at this stage. There may be first order phase transition, which also can give us information about the phase transition, because if you have first order phase transition, you have true vacuum bubbles, they expand, and the bubble walls, when they intersect, they can form false vacuum bag, which just is false vacuum with contains false vacuum with negative pressure, so it forms black hole. Primordial black hole evaporation is something what can give us information about black hole creation, even if they were not created, if we do not survive to present time, and it gives us some new sources of energetic particles in the period of the evaporation. It's very important to notice that together with particles for ordinary matter, they produce everything what exists in our space-time, and in that sense it's universal source, which may provide us the possibility to create super weakly interacting particles in the result of evaporation. Actually, we got used to the idea that we live in homogeneous and isotropic world, but does it exclude the possibility of strong primordial non-homogeneities? Actually, no. If this component corresponding to this non-homogeneous distribution is very tiny and strongly subdominant, then average effect of such strong non-homogeneity is rather weak and fits the estimation of the fluctuations of density, which are reflected in CMB fluctuations. The possibility of such strong non-homogeneities can be of two types. There may be phase transitions that gives us some unstable cosmological defects. Another possibility is that there is strong non-homogeneity in distribution of baryon excess created in baryon synthesis. And in extreme form, it gives us antimatter domains in baryon asymmetric universe. In cosmological phase transition, we either have such transitions at high temperature, or we have such transitions in at the inflationary stage, and then interaction of the heat field with inflaton gives us corresponding phase transition. And reminding Zeldovich, we can remind his solution of domain walls in his work with Zeldovich, with Kobzarev and Open. His idea about the in the case of continuous degeneracy, you have cosmic strings, and we discussed with him possibility of isolated singular points, and these isolated points in grand unified theory, these defects are magnetic monopoles with the corresponding problem. A simple U1 model just gives us the idea. It is the model which corresponds to the physics of axion-like models. So axion, when you have two scales, one of which is rather high, and another one just much smaller. And if we have this phase transition at the stage of the phase transition after reheating, then we have in such model first formation of cosmic strings, and then after the second phase transition takes place, which just gives mass to this phase, then it becomes some oscillating around true vacuum field, which possess properties which give us large-scale correlations, which we call archeoles, which just strong correlations, which gives us the possibility to put constraints on axions that matter. Alexander Dolgov today had discussed the Dolgov-Silk model, which just gives the possibility to explain how massive primordial black holes may appear. In case of axion-like scenario, you can have it if your first phase transition takes place at the inflationary stage, and then second phase transition just comes. It gives you some regions where you have another vacuum, and correspondingly you have closed walls. Collapse of these closed walls gives you the possibility of creation of massive black holes, and their mass is determined by two principal constraints. One of them is that the width of the wall should not be larger than the Schwarzschild radius of corresponding mass, so that you can fit all the wall inside the gravitational radius. It gives you minimal estimation, and maximum estimation comes from the point that if you have too large wall, then you have a possibility to dominate before this wall appears as a whole. So pieces of wall can dominate, and this region becomes superluminally expanding, because the wall-dominated universe just has a nice scale factor, which is square of time, so it will never reach this object. So it gives you principally maximal probability, and it leads to specific closed wall collapse, which gives us the estimation for the primordial gravitational wave background, which may be of interest for not only LIDA Virgo, but also for future LISA experiments. Now we have a gravitational wave transient catalog, which just gives us interesting possibilities, that there is a gives us the interesting possibility that there is a, some amount of events which were rather close in time one to another. And it's an interesting feature, because in this scenario we have a correlation, so that you don't have single black hole, and they are not produced randomly, but you have a cloud of primordial black holes, so that in this cluster you have a first of all, higher probability to form binaries, and the other point is that we have such a cloud which may have contain sufficiently massive black holes, and the recent results just show that there appear events in which can be highly explained by the evolution of supermassive stars. So actually, today, Anastasia Kirichenko just discussed the possibilities to probe existence of strong non-homogeneity in baryon excess, so that you have anti-baryon excess, and anti-baryon excess just if it is in sufficiently large region. This sufficiently large region is determined by diffusion of baryons and antibaryons to the border of this domain. And in this diffusion, we have annihilation, so that small domains do not survive in matter surrounding. However, if it is sufficiently large, and in terms of mass it is about 1,000 solar masses, then such object can exist. And something reminding what discussed is discussed in Dolgov's silk scenario is that if you have spontaneous baryosynthesis, then you may have average density, which is corresponds to baryon charge, which is positive, but you may have some regions in which you have excess of antibaryons, and it predicts the existence of the antimatter stars in our galaxy. And today, Anastasia Kirichenko discussed the possibility how we can probe it. Just it's an interesting story. You have some single source which gives you some background effect. So if you talk about antinuclei, then they are moving. So first of all, antimatter can annihilate, and it gives us contribution to gamma background. And another point is that it can produce anti-helium or heavier nuclei, and they can be can reach Earth, and should be detected in underground in the cosmic detectors. Amela, discussed today by Andrei Mayorov, just started to look for them. And first signal from antimatter has been announced in 2016 by principal investigator of IMS2, Professor Samuel Ting, and it was anti-helium free. And 2 years later, so now he claimed 8 clear single-track events with the charge -2 and in helium mass range. And also they have something what looks like anti-helium 4. However, the probability for this event is still not sufficient to exclude it as that it is background event. So we should wait some years when statistics will be significant to say something definite above 5 standard deviation level. So just to conclude, let me say that modern cosmology involves new physics, different mathematical candidates from different come from different motivations of the extension of the standard model and can coexist in multi-component dark matter. New stable and metastable particles, topological defects, primordial black holes provide proofs for physics of the early universe. Strong primordial nonlinear structures maybe just can explain what we see in gravitational wave detectors. And these proofs of new physics reflect the basic idea of cosmoparticle physics, developing legacy of Zeldovich and Sakharov in studies and fundamental relationship of cosmology and particle physics. The basic idea is that if you have new physical scale, this scale can be approached from below by experimental particle physics. It gives strong cosmological effect when it is around Planck scale and smaller, but in the mediate scales, you have possibility of astrophysical proofs for this new physics. And I'd like to finish just noticing that reminding Zeldovich we also can remind Andrei Dmitrich Sakharov. Next year, United Nations announced Sakharov years, and just I'd like to draw your attention that one of the possibilities to commemorate his 100th anniversary may be to discuss his legacy in this field. What I plan to do in the session, The Universe of Andrei Sakharov, at the first electronic conference on the universe in February, and it may be one of possible platforms for such discussions, though I think there will be many other events for science. So thank you for attention.
Thank you very much for this nice presentation, and thank you for being exactly in time. So we have a time for some questions. Please, if there is anyone who wants to ask a question. Okay, I see that Grigory Vershagin wrote in the chat, antibaryons can interact with cosmic rays, supernova remnants, etc. Are there any constraints?
Thank you for this nice question. Yes, it is just not only antibaryons can interact with cosmic rays, they can interact with matter, gas. And that puts constraint on the amount of antimatter in our galaxy, because just the pollution by antibaryons of the galaxy would lead to annihilation of dominant antiprotons with matter. And it can give the possibility to put constraints by gamma ray background, as I demonstrated, but very briefly and quickly on my slides. We can reproduce in this way for the amount of antimatter, about 100,000 solar masses. We can roughly estimate the gamma ray background which should appear, and it corresponds in the 10-100 MeV range to what was observed. However, we cannot say that it proves antimatter, because any source of pi0 gives you the same thing. So actually, the combination of different constraints certainly put constraint on this hypothesis, but it is something what is just need some proof, and well, my intention is to be prepared to the result which will be given by the IMS2, and so I just and we just try to approach from theoretical side to that.
Thanks. Thank you very much for this nice presentation. So if there is no any other question, we thank again Maxim Khlopov for this nice presentation. And once more, we thank all the speakers from this afternoon session. And I think this is the end, Gregory, yes? There is no any more presentation today.
Yes, correct.
Okay, very good. So bye, everyone. See you tomorrow morning. Thanks for this.
Thank you very much for very nice mediation of this session. And you, Grigory, for all. Goodbye.
Thank you. Thank you. I think this is the wrong program of Tuesday. We'll have Thursday tomorrow morning, and we will start with Nikolai Shakura at 9:30. Okay. Thank you very much.
Yes.
See you tomorrow.
Bye, everyone.
Thank you.
Bye. Bye.
Thank you. Goodbye.